What was that? Hey there! You want to hear the truth, son?
Hey there. These days, adequate care for and understanding of weapons is crucial for your survival. I'm gonna show you the chemistry of some basic survival techniques. Gunpowder's been pretty hard to come by these days, but any real survivalist knows that you can make your own gunpowder as long as you understand the chemistry. What you need is potassium nitrate, also called saltpeter, it's KNO3, sulfur, and charcoal. Some nasty stuff. You will mix them in a ratio of 5 charcoal to 1 potassium nitrate to 2/3 sulfur. Then you mix that bad Larry up real good. Potassium nitrate supplies the oxygen for the reaction, while combustion produces a large amount of CO2, which makes gunpowder very efficient. Potassium nitrate is a solid, and the carbon dioxide produced is a gas, meaning that the pressure increases and propels the bullet through the barrel. Charcoal is used as a fuel source for the reaction, and sulfur, now this sulfur is added to speed up the rate of the reaction. In this reaction, charcoal serves as the supplier of carbon. Charcoal is not a pure substance. It is a heterogeneous mixture of about 65 to 85% carbon and varied amounts of ash and hydrate. For this reason, the exact delta H, or change in heat, cannot be calculated. While it cannot be calculated in joules per mole, an average change in temperature can be plotted against grams of charcoal burned. The combustion of gunpowder is thermodynamically favored, meaning that the delta G is negative. This is because the delta S, or disorder, is positive and increases during the sublimation of a solid to a gas. Also, the delta H is negative, meaning that heat is released. Sulfur acts as a catalyst for this reaction, lowering the activation energy. Catalysts work by providing an alternative reaction pathway for the breaking and remaking of bonds. The activation energy for this new pathway is often less than the activation energy of the normal pathway. When a catalyst is present, one of the reactants, substrate, reacts with the catalyst, forming an intermediate product. The intermediate product then reacts with the other reactant to form the final product. Now, your gunpowder is ready to go. If you get hurt, you can apply H2O2 to the wound as an antiseptic. Gotta get it in there. H2O2 naturally reacts to form H2O plus O2. This reaction is, however, very slow, although it is spontaneous. There is an enzyme called catalase in human blood. This enzyme causes the rate of the reaction of H2O2 to speed up, which produces a much greater amount of H2O and O2 gas on the surface of the cut. The delta H of this decomposition reaction is negative 196.4 kilojoules per mole, meaning that heat is released. The positive delta S and negative delta H mean that the reaction has a negative delta G, which is thermodynamically favored. In my opinion, the worst part about the post-apocalyptic world is rust. As iron is exposed to air, it slowly but spontaneously reacts to form iron 3 oxide, which is also called ferric oxide. The reaction is 4Fe, which is a solid, plus 3O2, which is a gas, yields 2Fe2O3, which is a solid. It has a high EQ, which is the equilibrium constant. If you leave your metal weapons outside, prepare to remove the rust yourself. You can do this through electrolysis, which is the process of driving a non-spontaneous reaction to occur through the use of electric current. For this, you need a battery charger, water with sodium carbonate dissolved in it, a stainless steel anode, and your rusty metal, which acts as a cathode. When current is applied to the system, sodium carbonate is turned into sodium ions and CO3 minus 2 ions. Carbonate travels through the positive wire, while sodium travels through the negative wire. Ionic substances, when dissolved in water, conduct electricity, thus completing the circuit. The rusty metal then undergoes the non-spontaneous reaction that is the production of FeNO3. The FeNO3 then separates itself from the metal, and when cleaned, your rusty metal becomes brand spanking new metal. The electrolysis of rust is a redox reaction. The cathode, or rusty metal, is reduced, meaning that it gains electrons, while the anode, or sacrificial steel, is oxidized, meaning that it loses electrons. Each iron atom in the compound gains 3 electrons, while each oxygen in the compound loses 2 electrons to form iron plus oxygen, both with redox numbers of 0. Smoke bombs can help to impair the senses of your enemies, cats, and zombies. What you're going to need is sugar. You can use glucose or table sugar, something like that. KNO3, which is also called potassium nitrate or saltpeter, and something to cook it in, and a mold. You're going to want to mix 1 pound of sucrose with 200.964 grams of KNO3. Heat your container on your rugged outdoorsman fire and stir. Potassium nitrate, as seen in the gunpowder reaction, provides the oxygen needed to produce CO2 during combustion. The sugar slows down the burn and provides cheap organic material to produce a smoky burn. The KNO3 is the limiting reactant. Therefore, changing the amount of KNO3 will change the properties of the burn. Due to the fact that more KNO3 is used than sugar, 1.5 times as many moles need to be added so that they burn equally. Here's our finished product. chemistry. What are we doing here?
I need to tell you the truth.
About what?
I met a guy. He knows how the
Oh, yeah?
world ended. Yeah. He lives in Canada, though, so we're gonna have to get there.
We're in Texas.
Yeah, that's why I need you. I need your help. I need you to
I
drive.
only have my permit.
Oh, and I can't drive other people yet. Oh, it's okay. I know a guy. Let me make a call.
Alright.
Siri, call Charlie.
Hey, what's up, my home dog?
I need a ride. On the wild side.
All right, I'll be there on the triple.
Hey, Charlie.
What's up, guys?
Charlie, what happened to your arms?
Oh, it's a long story. I'll tell you on the way there.
Charlie, you sure you can drive like that?
Oh, yeah, I can... No, I can't!
It's okay, buddy. Oh, I'm good.
Hey guys, what are you gonna do in the apocalypse when that piggy bank you've been keeping, all the money no longer holds value? And all the guys down at the power plant have been either vaporized by nuclear explosions or eviscerated by giant cats. Well, I have a solution for both of these problems. A battery. I'm gonna use all the money I've saved in my piggy bank to make a super powerful battery capable of powering a dimly light LED light bulb. The ingredients you need to make this battery include a penny, a nickel, cardboard or paper, lemon juice, and salt. First, take some lemon juice, some salt, and mix it together. This is the solution you're going to use to soak your paper and cardboard in. The lemon juice acts as an electrolyte in the battery, and the salt acts as a sort of salt bridge within just the filter paper itself to keep all the paper neutral and make sure the reaction keeps going on. Next, cut out little circles in your cardboard or filter paper about the size of a penny and soak those in the lemon salt solution. After those have soaked for about 5 minutes, you're ready to start making your battery. First, take a nickel, one of the pieces of paper, and a penny. That completes one cell of the battery. Repeating this process yields higher voltage and allows you to light a light bulb. And here's the finished battery, all taped. And look at that light bulb. The electrolyte is what allows the flow of ions through the battery. So, to increase the lifespan of your battery and make sure the electrolyte doesn't evaporate, you can tape your battery and keep the electrolyte in. But what is the chemistry behind the battery? Well, basically this is a redox reaction with two half reactions occurring at both ends of the battery. At the anode, nickel atoms are being oxidized and forming nickel ions, and the two electrons are flowing to the penny at the cathode, where two hydrogen ions from the citric acid are being reduced by two electrons and turning into hydrogen gas and escaping the battery. The whole reaction for this process is nickel atom plus two hydrogen ions yields a nickel ion and hydrogen gas. This produces 0.25 volts in every cell. This is calculated from adding up the voltage potential of the two half reactions, and with nickel having a voltage potential of 0.25 and hydrogen having a voltage potential of 0. The voltage can't be increased by increasing the size of the nickel or the penny or the paper in between. It can only be increased by adding more and more cells onto the top or bottom, so the voltage gets added up from each of those cells. And with enough cells, you can power a light bulb or a city. Another key factor in the apocalypse is transportation. Whether it's fleeing from zombie hordes, scouting out other survivors, or scavenging resources, transportation is an important part of everyday life before and after the apocalypse. Today, I'm going to explain the chemistry behind these motor vehicles. Most vehicles have an internal combustion engine which runs on gasoline. Gasoline is a complex mixture of different hydrocarbons consisting of alkanes, hydrocarbons which contain only single carbon-carbon bonds, but also a few alkenes which have double carbon bonds, alkynes which have triple carbon bonds, and aromatic compounds which contain a benzene ring. Single bonds contain a single sigma bond, while double bonds contain one sigma bond and a pi bond. And triple bonds contain a sigma bond and two pi bonds. The stronger the bond, the more energy it takes to break apart, and the less energy is released by that hydrocarbon when it combusts. These bonds are covalent, as the electrons are shared between the atoms but not transferred. And while gasoline is primarily nonpolar, there are very few polar molecules in the mix. There are a range of different hydrocarbons with multiple isomers in gasoline. The structure of the hydrocarbons has quite an effect on how well the gasoline performs, rated by its octane number. Straight chain hydrocarbons, such as heptane, C7H16, are prone to pre-ignition, and which causes engine knocking and damage to your vehicle, while branch hydrocarbons, such as isooctane, C8H18, burn smoothly and deliberately. Gasolines produce energy through a combustion reaction, where the hydrocarbons react with oxygen to release energy and produce carbon dioxide and water, such as in the following reaction with octane. This process is exothermic because the energy required to break the bonds in the hydrocarbon and the oxygen is less than the energy that is released by the formation of the bonds in the carbon dioxide and the water. The delta H, or change in enthalpy, for this reaction is negative 10,948 kilojoules. And so the enthalpy, so the heat of combustion for octane is negative 5,474 kilojoules per mole, and that converts to 47.92 kilojoules per gram. Gasoline, however, is not pure octane, and the average heat of combustion for gasoline is 45 kilojoules per gram. That is assuming the gasoline goes to complete combustion. If not enough oxygen is getting to the reaction, the gasoline will instead go to incomplete combustion, releasing less energy and carbon monoxide instead of carbon dioxide. The internal combustion engine uses the energy released by the combustion of the gasoline to power a piston. The process can be explained by PV equals nRT. As the mixture of gasoline and oxygen is compressed into the piston, it occupies a very small volume and is ignited by a spark plug, causing the activation energy of the reaction to be met and the combustion to begin. As it combusts, the increase in temperature causes an increase in pressure. As it can be seen, the pressure and temperature are directly related in PV equals nRT. And the pressure of the gas pushes the piston down to convert the thermal energy released into kinetic energy for the movement of your vehicle. The resulting gases are not heated up as much as the stoichiometry says they will be, because most of the energy is used to push the piston. The more the gasoline-air mixture is compressed into the piston, the more efficiently the fuel is burned, because there is a greater mechanical energy output versus thermal energy output. But the more the mixture is compressed, the more likely it is to pre-ignite solely because of the heat and pressure instead of the spark, causing engine knocking, which is why higher octane gasoline is used for high performance vehicles. And that's your basic rundown of energy in the apocalypse. Hey, look out, Piggy! That's highly explosive! Oh my god! Where are my hands? Wait, there they are!
Oink, 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 oink.
Okay. Well, we're here now.
Wow, I can't believe you drove this way with no arms.
I know. I'm a one-man army.
So who is this guy? He's a guy that knows why the world ended.
How does he know?
Because it's all his fault. Yep. I done it. How's it going, Django? The J is silent. Django? Yes. It wasn't the apocalypse yesterday. It isn't the apocalypse tomorrow. It's the apocalypse meow! What kind of monster could have created such a destructive force? First, there was dynamite. Then, Harbor created the chemical weapons. And then the bomb! The nuclear bomb! Now, we have to face the fury of those damn dirty cats. It's a frickin' catastrophe! Was it some government bent on world domination? Was it possibly some secret terrorist group? No! It was us! The world was perfect, and we were complacent. It was our own apathy that caused the destruction of the ozone. What's the chemistry of the ozone? Oh, well, let me tell you a tale. 17 years ago, the Industrial Revolution began. This began the mass production of greenhouse gases, such as CFCs. CFCs break down the ozone layer. Ozone is O3, presented by this resonant structure right here. Ozone is created by something called the Chapman cycle, as displayed right here. Diatomic oxygen plus atomic oxygen is equal to ozone. This cycle is also broken down by UV radiation. Oxygen plus UV radiation equals atomic oxygen, and ozone plus UV radiation yields atomic oxygen and diatomic oxygen. Ozone is not formed like regular molecules. It starts out with a diatomic oxygen and a regular oxygen atom. But this regular oxygen atom goes through some changes before it becomes ready to create ozone. Here, you can see a regular oxygen atom. This oxygen atom collides with the nitrogen atom to change its electron configuration. As you can see, here is the electron configuration of a regular oxygen atom. 2s2, 2px2, 2py2, and 2pz0. This means that this orbital has not been filled. When it collides with the nitrogen atom, it hybridizes and transfers one electron from the 2py orbital to the 2pz orbital. Now, this oxygen atom is ready to become an ozone. This newly formed atomic oxygen reacts with the diatomic oxygen to form ozone. And this special oxygen atom becomes the central atom in the resonance structure. Greenhouse gases destroy the ozone. Well, how does this happen? Well, here is your common CFC molecule, or chlorofluorocarbon. It has a carbon in the middle attached to one fluorine atom and 3 carbon atoms. This is a very stable molecule. When we produce it by things like air conditioners, refrigerators, and any heating or cooling system, this molecule can be released. As it rises into the stratosphere, it succumbs to UV radiation, similarly to the ozone. When the UVB light hits the bond between the carbon and the chlorine atom becomes free. The chlorine atom then, because of its high electronegativity, pulls apart the oxygen atom from the ozone to create a hypochlorite ion, as well as diatomic oxygen. This hypochlorite ion reacts with atomic oxygen to yield a chlorine atom and diatomic oxygen. This process uses up what little concentration of atomic oxygen that's in the stratosphere. This prevents more ozone to be formed. Already, not a lot of UV light hits any of these molecules. So, without any atomic oxygen, no ozone can be formed. Ozone typically blocks the UV radiation that hits the Earth's atmosphere. As seen from here, both diatomic oxygen and ozone contribute to the shielding from the UV rays that hit the Earth. Ozone layer, no radiation from the sun could be blocked from hitting the Earth's surface. So, this is when things got real. The UV rays started getting into the Earth's surface and happened to hit the cats. The cat's DNA mutated from those UV radiation. They started to grow, first as tall as deer, then as tall as horses. With their size came the true primordial beast inside of them. They began to attack humans. The government wasn't doing anything about this. They were just letting it go by like nothing was happening. So I was left with a choice. Do I sit here and watch as humans be devoured by cats? No, I wasn't gonna have that. So I snuck into the White House and pressed the button. I released the nukes. Nukes release radiation. There are 3 main types of radiation rays and 2 main types of radiation. There is ionizing and non-ionizing. The radiation rays are alpha, beta, and gamma. Alpha is a non-ionizing radiation ray. It is basically composed of a helium atom with a +2 charge. It consists of 2 protons and 2 neutrons. This is a very weak ray of radiation, as it can be stopped by paper. Beta radiation is a little bit stronger. It is made up of electrons or positrons, which are the antiparticle of electrons. This radiation can be stopped by an aluminum sheet. And then we have gamma radiation. This is the stuff that comes from the bomb. These are photons, and they can only be weakened by lead plates. All types of radiation will cause mutations in DNA and can certainly cause death. The cats, however, they didn't die from this radiation. They absorbed it, and they grew even bigger, now as tall as buildings, and becoming even more vicious. And then, this is when the government finally decided that it had to do something about this chaos. They weren't going to let building tall cats just roaming the world. No. When they finally decided to make a decision, they realized all their nukes were gone. Mostly because of me. And the nukes didn't even work. They just killed more humans. So they switched to chemical weapons. There are 4 main types of chemical weapons: chokers, blisters, blood agents, and nerve gases. Chokers are things like chlorine gas and phosgene gas. Chlorine is just diatomic. Phosgene is made up of chlorine, carbon, and oxygen. Chokers inhibit the body to make muscle contractions in the lungs, so therefore your cells cannot perform cellular respiration. This means you die from lack of energy.
Blistering agents include mustard gas and Lewisite gas. These cause giant growths filled with liquid inside and outside of the body, which will inevitably kill the victim. After that came the blood agents. A gas that classifies as a blood agent is hydrogen cyanide. Blood agents prevent cellular respiration as a non-competitive inhibitor. Hydrogen cyanide can also be used for electroplating as well as making nylon. Low doses of it will kill a human in a minute.
One example of a nerve gas is VX gas. VX gas goes into your nervous system, preventing signals being transferred from your brain to your muscles. Muscle twitches, nausea, and vomiting are common symptoms of nerve gas, as well as death. The lethal dose of VX gas is 10 milligrams. If you happen to go outside during this apocalypse, be sure to bring a gas mask everywhere you go.
They're here!
What?
Thank God!
Run! 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 Run!
Demon, fighter of the night, man, champion of the sun. You're a master of karate and friendship for everyone. Demon, oh, fighter of the night, man, oh, champion of the sun. Oh, you're a
Hey everyone, we've heard a lot about killing zombies and making explosives in the post-apocalyptic world, but what about the home front? I'm here today to tell you about the truly exciting parts about living in the apocalypse, such as baking cookies, purifying water, and how to make fertilizer for your garden. In a dangerous world, we need to use our knowledge of the world in order to survive. For instance, baking cookies, we need to know the chemistry behind it, so that we're able to make the first batch of cookies the right way. No need for second attempts. You don't want to waste your resources in the apocalypse. The first step in baking cookies is understanding that the ball of dough is a heterogeneous mixture. The dough is not a new ingredient, but a pile of other ingredients. When the cookie is first put into your post-apocalyptic oven, the butter begins to heat up and melt. Butter is an emulsion, which means it's a mixture of two immiscible liquids. The water and butterfat in the butter are miscible because the water has polar covalent bonds, while the butter has nonpolar covalent bonds. The butter starts to melt at roughly 35 degrees Celsius, which causes the cookie to begin spreading out. The water in the butter emulsion is released and starts to steam and boil as the vapor pressure of the water reaches 1 atmosphere of pressure. The water vapor expands as the temperature increases, according to Pervner, and so as the water vapor starts to be released from the cookie, it creates air bubbles, making the cookie flaky. The baking soda, or sodium bicarbonate, acts with acids in the dough to create CO2, which creates additional air pockets, making the cookie even fluffier. The baking soda is a base, and reacts with the acid to help make the final product neutral. It reacts in the following equation.
That's it.
When you add water to baking powder, the dry acid and base go to solution and start reacting to form carbon dioxide bubbles. Double-acting baking soda produces carbon dioxide bubbles again when it gets hot. This happens because although it is thermodynamically favored, it needs heat to help overcome the energy of activation. Next, Maillard reactions occur at 310 degrees Fahrenheit. These reactions involve the breakdown of proteins and sugars. The amino acids and parts of the sugar molecule then combine to create molecules that reflect certain colors of light, giving the cookie the brown color and the sweet aroma. Caramelization also occurs at high heat, as it's hot enough for the sugar molecules to begin breaking down, as the hydrogen bonds in it are broken apart. These molecules then rearrange themselves to make tasty caramel. If you want a darker cookie, don't use white granulated sugar because it doesn't work well with the Maillard reactions. Also, for a fluffier cookie, use more baking soda, as the increased amount of carbon dioxide will make the cookie expand more. Also, for a fluffier cookie, use more butter, as the water in the emulsion will steam and expand to make the cookie fluffier. Next, we're going to make the cookie, and for this, the gloves are coming off. Make sure you use a whole stick of butter so you get the emulsion. And then the egg, so you get the proteins that help to form in the Maillard reactions. Cookies. Next, you begin stirring it, so you get your nice, immiscible, heterogeneous mixture. And then, we'll make the cookie.
Doomsday.
We also need to learn about water purification to stay alive, or else you might as well be drinking your own piss. Might as well. The water we drink isn't pure water, but before we drink it, there are certain things we need to take out to make it safe to drink. Water samples may include ions, dissolved gases, and other natural dissolved molecules. Dissolved molecules from human activities, such as industrial wastes, are also possible to find in water. How do these molecules get into the water supply? Well, they mostly start off as solids, but are then dissolved in the water. What are the microscopic events that occur to allow these solids to dissolve in water? Well, first, favorable electrostatic reactions, as well as increased entropy. If the sums of these effects are stronger in the solute than in the crystal will dissolve. To begin, you can start with water that you collect from the lake, and you can remove large debris, as seen here, simply by screening it. Then, if you let the water sit for a while, insoluble particles that don't have polar covalent bonds like water and are immiscible will slowly separate, such as sand or oil. Some smaller particles that are insoluble will separate too slowly from the water and won't simply separate if you leave it there to sit. For this, you can add coagulants. These combined with the ions that are, or the particles in the water that are too small to just simply separate on their own, and will form a solid precipitate with it. Some particles are soluble in the water, and so these won't come out through coagulation or by simply letting it to become sediment. And so what must be done for this, for particles such as calcium ions, which cause water hardness and can help the growth of harmful bacteria, you need to add something that will act like a sponge and form a solid precipitate with that ion, allowing it to be removed from the water. For aqueous solutions, such as Bear Grylls Kool-Aid, you can use the concepts of Beer's Law to figure out how many harmful chemicals are in it, so you can then remove those from your water.
Beer's Law is the linear relationship between absorbance and concentration of an absorbing species. It is written as A equals ABC, where A is the absorbance, the small a is a wavelength coefficient, and B is a path length. C is the concentration. A colorimeter can be used in conjunction with Beer's law to help determine the concentration of a certain chemical in water. The colorimeter measures the amount of light transmitted through the solution, and by using known concentrations of a chemical to create an absorbance concentration curve, it is possible to then use Beer's law to help determine if the water is safe to drink. This is possible because A and B are constant, so there is a directly proportional relationship between A and C that forms a line. This graph shows how it is possible to plot the sample concentrations of a nickel sulfate solution, a harmful chemical in amounts bigger than 0.12 molar, against absorbance. With the best fit line, it is possible to convert A equals ABC to Y equals MX plus B to plot any further absorbances of a nickel sulfate solution in relation to concentration. This way, as long as you can find a colorimeter, you can check the concentration of certain harmful chemicals in your drinking water. Distillation is another method that you can use if you have the proper equipment to help purify your water. It works with insoluble as well as soluble components in your water supply. Distillation is a widely used method for separating mixtures based on differences in the conditions required to change the phase of components of the mixture. To separate a mixture of liquids, the liquid can be heated to force components, which have different boiling points, into the gas phase. The gas is then condensed back into the liquid form and collected. This diagram shows the distillation of salt from water. Salt is a soluble component, so it can't simply be screened out, but through distillation, the water goes to gas phase and then can be recollected without the salt in it. This diagram shows how the boiling point of water can be changed based on temperature and pressure. This way, so with this, depending at your altitude, you might have to use a boiling point that is not 100 degrees Celsius for your water. This diagram shows water boiling. Boiling occurs when the vapor pressure becomes high enough in the water that it equals or is greater than the atmospheric pressure, so then the bubbles in the water can then rise out in the gaseous phase. Note, boiling point can be changed based on what solutes the water has in it, because, for example, salt water will have a higher boiling point. Hopefully with this information, you'll be able to get clean drinking water in the post-apocalyptic world.
The last thing you need to know about surviving the apocalypse is how to grow your food. You need to ensure that you'll have a steady supply of tasty, crunchy edibles.
Hey there. I'm here today to teach you about how to use those giant abandoned industrial plants in the post-apocalyptic world to do the Haber process, which will supply all the nitrogen you need for your plant garden.
Let me explain what the Haber process is, so that you're able to make use of those giant abandoned industrial power plants. The Haber process combines nitrogen from the air with hydrogen derived mainly from natural gas into ammonia, so that you can use this ammonia as fertilizer for your plants. The reaction is reversible, and the production of ammonia is exothermic. The enthalpy in the delta H for the reaction is negative 92 kilojoules per mole. The pressure of the hot Haber process varies from one manufacturing plant to another, but is always very high. The Haber process uses 3 moles of hydrogen for every 1 mole of nitrogen. This process occurs as an equilibrium reaction, meaning that not all of the reactants are used up, and that it is reversible. You want to create as much ammonia as possible, so you want to push the equilibrium as far to the right as possible so that you get the most amount of a product. Because the reaction is exothermic, it's possible to use Le Chatelier's principle to help move this more to the right by lowering the temperature. This causes stress on the system, and the system will respond by moving the position of equilibrium to counteract this. In other words, producing more heat, and as a forward reaction because it is exothermic, it will create more product. However, the lower the temperature you use, the slower the reaction becomes. So it makes no sense to get a high proportion of ammonia if it's going to take years to produce that. Because of this, you have to compromise and use a temperature of about 400 to 450 degrees Celsius in order to produce a relatively high proportion of ammonia, about 50%, but it will be produced in a very short time. The pressure is very high because if you notice in the reaction, there are 4 molecules on the left-hand side, but only 2 on the right. And this means there's a higher pressure on the left side of the reaction. So again, according to Le Chatelier's principle, if you increase the pressure,
the system will respond by favoring the reaction which produces fewer molecules in order to get that back down. So it will cause the pressure to fall again. And so in order to get as much ammonia as possible in the equilibrium mixture, you need as high pressure as possible. 200 atmospheres of pressure is very high, but not amazingly high, and it's possible to achieve with what you might be able to find. Again, you have to consider the rate of the reaction when you're trying to produce as much ammonia as possible. Increasing the pressure brings the molecules closer together, and in this particular instance, it will increase their chances of hitting and sticking to the surface of the catalyst where they react. The higher the pressure, the better in terms of rate of a gas reaction. The higher the pressure seems to be good so far, but economic considerations mean that it is very expensive to produce and maintain that high pressure. And that is why only 200 atmospheres of pressure is used. I've been saying that there's a catalyst in the reaction, and although a catalyst does not affect where the equilibrium is, because the reactions are occurring at the same constant rate, the catalyst helps to speed up the reaction so it doesn't take as long to produce the ammonia. Because without the catalyst, the rate of the reaction is so slow, it virtually doesn't happen at all. You're able to separate the ammonia from the reaction chamber because when the gases leave the reactor, they are very hot and at a very high pressure. And ammonia is easily liquefied under pressure as long as it isn't too hot, and so the temperature of the mixture is lowered enough for the ammonia to turn to a liquid. The nitrogen and hydrogen remain as gases even under these high pressures and can be recycled back into the reaction chamber.